Hello everyone, this is Tanima. You're watching this video in my YouTube handle at the rate @Tanima_Barbie. Just to let you know, my YouTube venture is totally a personal endeavor as a voluntary virtual social outreach, and it has nothing to do with my profession, where I'm engaged with research and teaching in the field of molecular biology and biotechnology in an institution in India. I personally believe that education should be freely accessible to all. This is my second video on cancer biology. In continuation to my previous video, the present video discusses few perspectives of unlocking phenotypic plasticity in the topic of hallmarks of cancer. This video partially discusses the paper entitled Hallmarks of Cancer, New Dimensions. The DOI of the same has been pasted in the description box. Keep watching. Let's look into the first hallmark of cancer, that is unlocking phenotypic plasticity. During organogenesis, the process where cells develop, determine their roles and organize into tissues for maintaining homeostasis, they undergo terminal differentiation. This is when progenitor cells, often permanent, stop growing once these processes are complete. Consequently, the differentiation typically acts as a barrier to continuous cell proliferation, which is crucial for tumor development. Increasing evidence shows that overcoming the usual limits of cellular plasticity to avoid or escape terminal differentiation is key to cancer development. This plasticity can manifest in various forms. For example, early cancer cells from a normal cell nearing full differentiation may revert to a progenitor-like state. Alternatively, cancer cells from progenitor cells may bypass full differentiation, staying in a partially differentiated state. Additionally, transdifferentiation can occur where cells committed to one developmental path switch to a different one, gaining new tissue-specific traits not originally intended. These examples highlight that different forms of cellular plasticity collectively represent a distinct hallmark of cancer. What is dedifferentiation? Colon carcinogenesis is a prime example of disrupted differentiation. Early cancer cells need to evade terminal differentiation and exfoliation. This can happen through dedifferentiation of colonic epithelial cells that haven't yet become permanently differentiated, or by blocking differentiation of progenitor or stem cells in the crypts that produce these cells. Both differentiated and stem cells can be origins of colon cancer. Two developmental transcription factors, HOXA5 and SMAD4, are highly expressed in differentiating colonic epithelial cells but are typically lost in advanced colon carcinomas, which then express markers of stem and progenitor cells. Studies in mouse models show that forcing the expression of HOXA5 in colon cancer cells restores differentiation markers, suppresses stem cell traits, and reduces invasion and metastasis. This explains why HOXA5 is often downregulated in cancer. SMAD4 enforces differentiation and suppresses proliferation driven by oncogenic WNT signaling. Its loss, which is engineered in models, leads to dedifferentiation and WNT-driven hyperproliferation, explaining its common loss in cancer cells. The absence of both HOXA5 and SMAD4 leading to dedifferentiation is linked with acquiring another cancer's traits, making it challenging to strictly define this disruption as a separate and independent hallmark of cancer. Another piece of evidence involves the suppressed expression of MITF, a key regulator of melanocyte differentiation, which plays a role in the development of aggressive malignant melanoma. The loss of this transcription factor leads to reactivation of neural crest progenitor genes and the downregulation of genes characteristic of fully differentiated melanocytes. This indicates that these cells revert to their progenitor state from which melanocytes originally developed. A lineage tracing study of BRAF-induced melanomas identified mature pigmented melanocytes as the cells of a region, which dedifferentiate during tumor development. The mutant BRAF oncogene present in over half of cutaneous melanomas induces hyperproliferation that occurs before and is mechanistically separated from the dedifferentiation caused by the downregulation of MITF. Another study highlighted the role of ATF2, whose upregulation in melanomas suppresses MITF, contributing to the malignant progression of dedifferentiated melanoma cells. Conversely, melanomas expressing mutant forms of ATF2 that cannot repress MITF remain well differentiated. So friends, hope this video could throw some light on the first hallmark of cancer, that is unlocking phenotypic plasticity. Please don't forget to like and share my video and also subscribe to my channel. Here I would like to mention that the references that were used for preparing the video have been pasted in the description box, and if you're interested to look into the details, you might check the same. Meet you soon with yet another video on cancer biology. Till then, take care. Keep up. Bye.